Hey guys, little delayed on this video. Didn't we all enjoy that fun fire drill? Maybe not a drill, actual fire, whatever. Okay, we're on to a new section here. So we're moving into 6.2, which is volumes. And let's start off with the definition of how we're gonna find volumes here. So we're gonna let S be a solid that lies between X values of A and B. If the cross-section area of S in the plane PX, that just means the plane perpendicular to X. So that's X perpendicular to the cross-section, that's that PX plane. Where A of X is a continuous function, then the volume of S, which remember was your solid that we were spinning, is this. Volume equals integral from A to B of a cross-sectional area with respect to X. Super confusing, right? Even sit, reread it again. It makes a lot more sense once we do problems. So let's start off by just like doing some problems and seeing how it actually looks, and then I'll keep relaying it back up to this definition. So our first example we're gonna look at is we want to find the volume of the solid obtained by rotating about the x-axis, the region under the curve, y equals square root of x from 0 to 1. So the first thing we gotta do with doing this is draw a picture. So I have a nice little picture here for us of the square root of x, right? It's one of those functions from 0 to 1. Now, we are rotating this thing about the x-axis, which means if we were actually to take this function that I have here, I'll kind of highlight it in purple. And if we were to actually spin it, that means that underneath, that same thing's happening. And that since it's spinning about the x-axis, we're getting this 3D shape, which kind of looks like a cereal bowl on its side, maybe like a football chopped in half, the end of a loaf of bread, like a baguette or something like that. That's what this shape is kind of looking like. But now we're looking to be able to find this exact volume. And remember, our formula here is we want to take an integral of a cross-section of areas. And since we're spinning around the x-axis, our cut or our cross-section here is going to be perpendicular to that. So what that means is imagine we took a knife and kind of cut through this solid shape here and took the shapes, and if we just kind of split it open and we wanted to look at what that cross-sectional shape is, well, that shape here, if we actually took this and kind of looked at it, would be a circle. So imagine taking a bunch of different circles that fit through all these cross sections and we stack them up. Think like pieces of salami or something when you stack them up. You stack them up, it makes that whole salami you see sitting in Tops or Wegmans where they go and cut it. That's what we're working with here. So we want to add up all these little circles to make this 3D shape. Now the question becomes, well, what is this circle? Because we want to find the area of it, right? That's that A of X we're going to be looking at. Well, we had to think, how do we find the area of a circle? That's just pi r squared. The question now becomes, for this random cross-section that we take, how big is that circle? Because think it's always changing, right? The circles over here are real tiny, whereas the circle at the end is way bigger than that little one that would be at the beginning. So we need a general formula for this, and that's where the equation comes into play. What's the distance from the center to the outside, which is the radius? Well, that's actually just our function here, the square root of x. So our radius here is the square root of x. So our area formula that we're working with is just pi x. So we've actually developed a nice area formula that no matter where we would slice this perpendicular to the x-axis, we have a perfect area formula for it. We now want to actually do this equation though. So our volume here is going to equal the integral of, I'll write the whole thing normally. Right, that's our definition one. So what we're doing here is we're going from, well, where's our x bounds? From 0 all the way up to 1 we're adding. So it's from 0 to 1. Our area we just determined of this cross section is a circle with this formula, pi x, and it's dx. So actually pretty easy integral to have here. The pi is a constant, so the x is going to go squared, the half comes out front, and we're going from 0 to 1, which is just going to get us pi over 2. Nice. And so the thought to have here is whenever we're spinning around the x-axis with respect to the x-axis, it's going to be dx, because those cross sections are going to be perpendicular to the x-axis, going back to our definition up here. Okay, hopefully that example wasn't too bad. Let's do one more here. In this one, we want to find the volume of the solid obtained by rotating the region bounded by x equals y to the third, y equals 8, and x equals 0 about the y-axis. So if we're spinning this about the y-axis, let's start off by actually looking at what this thing even looks like. So our function here is the cubic, which I have drawn here. But then notice it says it's also bounded by y equals 8, which is this one. And what is that? X equals 0. So we have this shape specifically. And it says we are spinning this, rotating it about the y-axis. So when we're spinning this, it's going to spin around here. So imagine this shape. It's like a tall, skinny vase or something like that, with kind of a rounded bottom. Okay. So the difference in these two problems is we spun around the x-axis here, whereas here we're spun around the y-axis, which makes me think in my head right away, oh, if we're going to integrate this from a to b, this is going to be with respect to y, because we're spinning around the y-axis. That's generally how they work. But we also have to look at what our cross-section area is going to be, what that area formula is. So think if we slice this through and kind of took this and broke it open as well, what shape is there? It's another circle.
Mr. Bowman, may I ask you?
So as we're doing this, it's still a circle, and we're still looking for kind of what our radius would be here. So we're thinking, is there something from the center to the outside that we have here to get our area formula? Because we know in general, area is pi r squared. And that's still true, but we want this in terms of y. So what's this radial distance? Well, that's going to be represented with our equation that we have here. Since it's y equals x to the third, we actually need to alter that a little bit and make it x equals. And x there is going to equal the cube root of y. So using this in our area formula here. Oops, sorry. Cube root of y is our radius. So we need the cube root of y squared. Which if you want to just write in a neater, kind of more clean fashion, that's y to the 2/3. So now we have our area is pi y to the 2/3. And think, since we have that area of that one kind of salami slice as we kind of go through it and we're trying to stack them all up, we need to put that in our formula here. By the way, you should have seen the stink face I gave T Little when he walked in, interrupting here. It was amazing. So that's our pi r squared here. And this is with respect to y. Now the question is, what are our y bounds? Think the lowest one here, 0, 0, and it goes all the way up to y equals 8 here. So our bounds are 0 to 8. Let's go through, integrate, do the thing. So we're adding 1, becomes 5/3. That means 3/5 come out front, and we're going from 0 to 8. And then when we plug in 0, That's going to be 0 as well. It's easier to take the cube root of 8 first. The cube root of 8 is just 2. So we have 2 to the 5th, which I believe is 32. Am I right in that? Or 1632? I think so. Then we need 32 times, that's a 3. That's going to get us what? 96 pi over 5. Number's not quite as nice as maybe the pi over 2 up top, but hopefully the process is making sense. The difference between spinning around the x versus the y-axis. Okay, homeworks that we're going to look at. We're in the new section here, 6.2, and this is from what? I want 1, 2, what I wrote down the other ones, 5 and 6. We're going to look at 5 and 6, not 56. Okay, enjoy your weekend, everyone. I'll see you all back here on Monday.